When I first started exploring regenerative medicine, I expected to end up working on something big, like stem cells, bioprinting, maybe even creating a tiny organoid if I felt really ambitious. Yeah, so none of that actually happened. Okay, so to explain, while researching tissue engineering, I learned a tiny fact that derailed everything I thought I wanted to do. So I learned that most engineered tissues fail not because of the cells, but because the nutrients physically can't reach the inside. And suddenly that became the mystery that I wanted to solve. So I wanted to explore one clear, specific question. Could a scaffold, the kind used in heart patches, actually support nutrient transport deep enough to keep cells alive? Before I go further, I just want to quickly explain what a scaffold is. So, a scaffold is basically the temporary framework that cells attach to as new tissue grows. But the pores have to be open, connected, and arranged in a way that lets nutrients pass through. And if they can't, then the inside essentially becomes a dead zone. And so, that's exactly what I wanted to simulate. And so, the first step for that was designing a heart patch scaffold myself. So in this video, you can see me designing a 3D model of a scaffold in Tinkercad. So I started off with like a square flat base shape to get the overall size of the patch right. Added a curve to one side to mimic like the shape of a heart wall, and then I added hexagons to imitate like the honeycomb structure I wanted. And this is to show like the pores that were mentioned earlier. And so you can see me copy pasting just to get like all of them aligned properly. And then I'm just cleaning it up on the edges so that nutrients have clear entry points. And by the end, I'm gonna basically have this curved honeycomb scaffold that seemed realistic enough to test in a diffusion simulation. So you just see me cleaning it up on all of the edges, and this is the final 3D model. So once I finished the model, I converted it into this pore mask, which basically tells the simulation which parts are open for nutrients and which parts are solid. Then after gathering that, I ran everything in Google Colab. I made it so that the nutrients would start at the top, just like how oxygenated blood would reach a cardiac patch, and then they'd diffuse downwards through any connected pores. Okay, so the idea is actually quite simple. If the scaffold works, nutrients should slowly travel deeply over time. Okay, so now I'll be talking about the results from the actual simulation, which were in the form of heat maps and one graph. Okay, so step 0 is initial contact. Nutrients sit on the surface, which is nothing really surprising. Okay, so step 20 is shallow diffusion, and so they start spreading sideways, but almost none of the nutrients move vertically. And so this already tells me that the pore network isn't really giving nutrients a path forward. Okay, so step 60, the mid layer is still blocked. And so by this point, nutrients should be moving deeper, but you can see that they're basically still stuck near the top. This means that the honeycomb openings might look connected, but the geometry isn't forming actual channels for nutrients to move through. So step 120, the deep regions starve. And even after a long time, the bottom stays almost completely untouched. And so this is the point where a real tissue would fail, and the cells deeper inside wouldn't be able to survive. So looking at all 4 heat maps together basically tells us the whole story. Everything is happening at the surface, and the deeper layers never get those nutrients or light up, which means that the scaffold isn't giving nutrients any path to travel down. Okay, so this graph makes things even more clear. Nutrient concentration starts high at the top and then drops almost instantly, and by 30 to 40 pixels down, the concentration is basically 0. After that, the line stays flat all the way to the bottom. So this shows that the deeper regions aren't underfed, but they're literally not fed at all. To be fully honest, this whole process didn't turn out the way I thought it would, but it taught me a lot and completely changed the way I think about tissue engineering. I used to think the hardest part was the biology, the cells, the materials, and the growth factors. But you can have everything perfect, but if the geometry isn't okay, that alone can make or break a tissue. If nutrients can't reach the center, the tissue will never survive. So my next steps are now maybe to figure out how to actually improve a scaffold like this. Maybe with bigger interconnected pores, vertical channels, or tiny vessel-like networks. I also want to test simulations with active flow instead of just diffusion, and compare different designs side by side to see which ones actually transport nutrients deeper. This project started out with a small question about what happens inside engineered tissues, but it really helped me understand a huge challenge in regenerative medicine, keeping the inside alive and not just the outside. And honestly, that mix of all these topics combined, biology, physics, and design, is what makes this field so exciting to me. For anyone interested in reading my article on this project, it's linked in the bio. Thank you so much for listening, and see you guys next time.